For this video, I'll be walking you through how to implement a red-black tree using JavaScript. I'll be sharing with you everything you need to know about red-black trees and binary search trees in general, and show you how to handle every red-black tree related cases with ease. Let's get to it. I strongly encourage you to have watched or to go watch my videos on binary search trees and AVL tree for a much in-depth understanding of binary trees and things I'll be doing here. But I'll go in through some details about those trees here as it is required to understand a red-black tree. To start, let's first understand what is a red-black tree, why you need it, and how it came to be. Red-black tree is a binary search tree much like an AVL tree, and because of that, they share binary search tree properties that say a node has at max 2 child nodes as left and right nodes. The left node value is less than the node value, and the right node value is greater to the node value. This applies to all descendants as well, so the right side tree values are greater than the node value, and inverse is true for the left side. The structure of a binary search tree relies on the order of the node insertions, giving an average complexity of O log of n and a worst case scenario complexity of O of n, which is a limitation. You may have cases where one side can get too deep and unbalanced, like if you continuously insert node greater or less than the root. This will increase the time to find a node, which increases the complexity of operations, and that's why the worst case scenario is O of n. And because of this unbalanced nature, other variations started emerging like the AVL tree, which inherits the binary search tree properties. An AVL tree plays with the idea of a height of a node and the balance factor, where the height of a node on one side differ at most by 1 from the other. An AVL tree is a self-balanced tree, which means that the tree rebalances itself on insertion and removal of nodes, which is pretty cool. An AVL gives you an average and worst case scenario complexity of O log of n, and is considered to be a strictly balanced tree, which makes it great for lookups. So if you need a tree for frequent lookups and few insert and remove operation, this is your tree. This leads us to the red-black tree, which is not a strictly balanced tree, which makes it faster for insertion and removal operations due to its relative relaxing balancing nature. Red-black tree is actually a superset of an AVL tree, which means you can color an AVL tree nodes red and black and it will just work. And both have the same average and worst case scenario complexity, but red-black tree introduces new properties to the pile that really defines it. Every node is either black or red, but every node is inserted as red and recolored after if necessary. The root is always black. All nil nodes, aka the nodes which are null, are always black. If a node is red, all its child nodes are black, which means there's no red-red parent-child relationship, which makes it safe to assume that if a node is red, then its parent is black. And finally, the most important rule is that every path from a node to any of its nil descendant goes through the same amount of black nodes. This means that when I started at any node and traverse towards any nil nodes, I should count the same number of black nodes. And these rules drive the red-black tree, which makes it fun and somehow more elaborated to implement, as there are many cases to address. Now with this knowledge, let me show you how to implement this tree using JavaScript to further illustrate how awesome this tree is. Since this tree relies on color, I'll first create a frozen object with 2 colors I can use for this implementation. One thing I'll do different than my previous AVL and binary search tree implementation is create node class, which I'll call red-black node. I'll give it a private color method and start with the left and right node of null. The constructor will take an optional key and parent value, and which I'll use to set key and parent properties. This implementation will treat nil nodes as normal node, just so I don't have to spend time trying to figure out when the node is null versus a normal node. This will help with checks, as you will see, since all we care about is the color properties of a node, and the rules say that all nil nodes are black. So if a key is null, I'll set the color to be black, otherwise every node starts as red node, and if so, I'll set the left and right node to be the nil node instead of having left and right to be nulls. One thing about binary trees is the memory a node consumes. Because this is JavaScript implementation, I'm not concerned about memory, and I'll go ahead and include a couple setters and getters to help me with implementation. The first ones are isRed and isBlack getters to tell me if a node is red or black. Another useful one would be to know if a node is nil or not. So a isNill_getter will tell me just that. The color is private for a reason, so I'll set a getter to return it and a setter where I first check if a node is nil and avoid changing its color. This is because a nil node is always black, and this will make sure that even if I accidentally set a color on it, it will always be black. Now we got everything we need to start, so I'll go ahead and create our red-black tree with a private root property to set to null, then a root getter that returns it. I will not be extending the binary search tree as I did on AVL Tree video implementation, so we can just focus on red-black tree things. But in the link below, I'll leave you with the code with extending of binary search tree, which will include methods for lookup that you will need. On the binary tree, I have a create node method that returns an object. And on this one, I'll take an optional key and parent properties and return an instance of our red-black node. The advantage of this is that if later on I decided to change what create node method returns, I just have to change in one place. I'll first bring the print method from the other implementation to help us visualize things, but I'll do some changes since the nodes are different here. I'll change the null check, and if a node is nil, I'll just quit with the return. And I'll also add the color of the node in the log. Everything else remains the same. I'll go ahead and instantiate the tree and call the print method now to start. We will be focusing on the insert and remove methods override, starting with the insert so we can populate the tree. The insert takes a key which I'll use to create a node, and if root is null, I'll just set it as the root node. Otherwise, I'll call the insert node private property, which I'll bring over from our binary search tree implementation, passing the new node. Since I'm not extending the binary search tree, I'll change this comparison to not use the compare method. And also, since the nodes now have parent, I'll set the node parent as the current node after I do the insertion. Now let's insert some things in the tree. I'll go ahead and call insert and pass 10 to start, and we see the logs show 10 as the root marked by the star symbol, and it is red node with left and right black null nodes. The null nodes respect the red-black tree properties that say that nil nodes are always black, but the root is red, which violates the red-black tree property that says that root is always black. To fix that, I'll create a private method called adjustTree after insertion, which takes the newly added node, and I'll call it an insert node method after the insertion happens. The first thing I'll do is check if a node parent is null and set its color to be black, based on the idea that only a root node has no parent. With that, our root is now black, which now makes the tree valid. I'll go ahead and insert 18. As you can see, it is a red node with black nil nodes with a black parent, and so far no rules are violated. I'll add another node, and now the root node has 2 red children. Then I'll insert 15, which should go to the left of 18 since it is greater than 10 and less than 18. Like that, we violate a red-black tree property that says if a node is red, both of its child nodes must be black. In a red-black tree insertion operation, you should be concerned with the parent and uncle nodes. In this case, the parent node is 18 and the uncle node is 7. So in the adjustTree after insertion method else body, I'll grab the node parent and grandparent, then use the grandparent to get the uncle node, and uncle node can have 2 colors, either red or black. And since our latest node here has a red uncle, let's handle that first. In this case, I'll call another private method called handleRedUncle, and I'll pass the nodes parent, uncle, and grandparent because when a red node has a red parent and red uncle, we just recolor these nodes. So I'll make parent and uncle to be black and grandparent to be red. But notice that the root now is red, which violates another red-black tree property. And to fix that, I'll call adjustTree after insertion and pass the grandparent, which will fix our problems. Note that it is possible to have a red-black tree made up entirely of black nodes, which does not violate any property. Let's continue inserting nodes, and this time I'll insert 16, which should go on the right of 15. And again, we violate the red parent-child relationship, but this time our newly insert node has a black uncle. When a red node has a red parent and a black uncle, there are 4 situations we need to handle. It has to do with where the node is in relation to its parent position. The node can either be on the left or right side of its parent, and the parent can either be on the left or right side of its parent. I'll call this situation align and recolor, which pretty much comes down to align the node to the same side of the parent, recolor, rotate it in the opposite direction. In our situation, our newly inserted node is on the right side, but its parent is on the left side, so we need to align them both on the left side, then recolor and rotate the grandparent to the right, the opposite side. So if we rotate the parent to the left, it switches sides with the parent, making our new node the parent and the mid node between 18 and 15. Then we make our node black and its new parent red, then finally rotate the grandparent, which is now the parent, to the right, the opposite direction, which finally makes our newly inserted node the parent of what used to be its parent and grandparent. To show you all this, I'll first copy the left and right rotation methods from the AVL tree implementation and do some changes. For the right rotation, if there is a left node, I'll grab the node parent and keep everything else but not return anything. Because the nodes now have parent, I'll make the node parent the detached node. If the left node is not null, I make the node its parent. Now, if the node parent is non-null, which means this is not the root node, I'll attach the detached node either on the left or right side based on where the node was positioned. Otherwise, I'll make the detached node the new root, and finally set detached node parent to be the parent node. The left rotation is pretty much the same thing, but everywhere I mention left, I change to right. For our situation, I'll first do a left rotation on the parent node, then I'll create a private method that recolors the mid node, which simply makes the node black and its parent red. When we left rotate the parent, the node becomes the mid node, so I'll just right rotate its parent. Like that, our tree is now fixed with our node 16 black and parent of 2 red nodes 18 and 15. To get to the other situation, I'll need to make some strategic insertions, and the first one is 30. Then I'll insert 25, which will have a red parent and black uncle, but is positioned on the left of its right parent. So I'll do pretty much the same thing and just invert the left and right rotation. Now I'll insert 40, which will have a red uncle, so it goes through the first method to get the recolor, and then it continues from the grandparent, the node 25, which then gives it a black uncle, only this time it is on the right side of a right parent. So we just skip the first rotation and just recolor its parent. And then left rotate his grandparent node. To get to the final situation, I'll add node 60 and 2 to set up things, and I'll then add a node 1, and then puts 1 on the left side of the left parent with a black null uncle. Again, we don't need the first rotation, so I'll just recolor the parent node and do a right rotation on the grandparent. I'll go ahead and add 2 more nodes to set us up for the remove handling. Like that, all cases for insertion is now handled. Now I'll go ahead and add the remove method that takes a key and calls private remove node method. I'll just go ahead and copy the remove node method from the binary search tree to make a few changes, but first let me make you understand the 3 cases you need to go through to remove nodes. There are 3 types of nodes you can delete. A node with no child, one with either left or right node child, or a node with both of its children. On a red-black tree, we only have to do something when a black node is removed, because when we remove a black node, it will violate the property that says that path from a node to any of its nil node goes through the same amount of black nodes. And there are 6 cases where we need to do something about it. We also only act when we remove a node and not when we replace it. So when you request to remove an internal node, aka a node with child nodes, you actually are replacing it. So if a node to remove has a single child node, you replace it with the node it has and remove the node you used to replace it. When you remove the node with both child nodes, you must replace it with either the highest node on the left, aka the predecessor, or the smallest node on the right, aka the successor. But I prefer to use the predecessor, the highest node on the left. So I'll also bring over the max method and change it to also check if the node is not nil. On the remove node, I'll make sure to return when the node is nil or null. On the first two if statements, I'll just call the remove node method and not need to reassign it to the left or right nodes. Else, in the third if statements, this if statement is where we actually remove the nodes, and it's where we will do all our remove handling. So I'll first check if the node parent is null, which means that the root is being removed, and just set the root to be null. Else, if the node to remove was left node on its parent, I'll set the parent left to be a nil node using the create node method, and do the same thing if the node is on the right side, and this is what removes the node. The fourth if statement, I'll replace the node, and the way the replacement works is the node key is replaced with the replacement node key, which means that everything else about the node stays the same, including the color. And I'll set the node to be nil node and repeat this on the next if statement as well. One thing I want you to realize is when a node has a single node, it is clearly that the node is black and a single child is red. And when it comes to remove red, we just remove it without doing anything. The reason is that if a node with a single non-nil child was red, then it would need two black child nodes so it does not violate the red-black tree property. If a node with a single non-nil child was black with a black child, it would violate the path rule because you would have one extra black on one side. So whenever a node has a single non-nil child node, it is clearly a black node with a red child node. For the last else, we find the max node on the left, replace the key again, and then proceed to remove the replacement. Inside the if statements that does the deletion, I'll just call handle remove node within the node before we actually remove it, so we can use it to collect some information about its surrounding. In this method, the first thing we check is the color of the node, which brings me to the first rule of the removal. If you are removing a red node or root node, you just go ahead and remove it. We don't have to do anything about it. So I'll just make sure that the node is black and has a parent because only root has no parent. And like that, we handle the removal case 1. For the second case, I'll just call yet to create handle case 2 and pass the node. For when we were inserting nodes, we had to look for parent and uncle to decide how to act on the situation. But for removal, we need to look at the parent and sibling to make a decision. And for the second case, I'll create a private method that will return a sibling of the node, which I then call to get the node sibling. The second case is for when the node to remove has a red sibling, which automatically means that the sibling has a black child nodes and the parent is black. For that, we swap the colors of the sibling and parent, so parent becomes red and the sibling becomes black. If the node to remove is a left child, we left rotate the parent, otherwise we right rotate the parent. After all, I'll call a yet to create method handle case 3 with the node to continue our search. The third case is actually the opposite, which means everything is black, the parent, sibling, and the sibling's children. In that case, we make the sibling red and call handle remove node with the node parent. Because what we just did in case 3 is create a case 2 situation and we need to continue from the parent. Otherwise, I'll just continue by checking for case 4 by calling handle case 4. In this case, everything is black except for the parent. So all we gotta do is invert the colors of sibling and parent again, just like we did on case 2, but this time we'll do no rotations. Before we continue to case 5 and 6, let's play with this so you have a better sense of things working first. I already have here comment down nodes to delete to be able to check for cases, so I'll first remove 70, which proves the first part of the case 1, which if a node is red, we just remove it without changing anything around it. I'll also remove 17, which is also a red node, and again, the node is gone without anything around it changing. For next, I'll prove two cases, 2 and 4, by removing node 18. If you look closely, you can see that node 18 has a red sibling where both of its children are black and the parent node is black as well, matching the case 2 situation. So the parent and the sibling color swaps and the parent rotates left since the node removed was on the left. But now the node removed has a red parent and a black sibling, which matches the case 4. So we just swap the color of the parent and sibling. And to get to case 3, I'll remove 3 nodes, 25, 2, and 7, which will give me a tree with all nodes being black, which is a perfect for case 3. Which covers the case when the node to remove has a black parent and sibling children are black. So I'll just remove node 10, which will replace it with node 1. So the node 1 is marked for removal, and node 1 has black parent, sibling, and nephews. So node 15 becomes red, and case 3 continues the process from parent node, which is now node 1, and that again falls into case 3 since he has a black sibling and a parent. Therefore, the sibling becomes red, node 40. I remove node 1, which will get replaced by 15, and I'll remove node 15, which will trigger case 2 and 4 again. Like that, we create a perfect situation for case 5. In case 5 covers the case where the node to remove has a black sibling, and if the node to remove is a left node, and the sibling left node is red and the right child is black, we swap the color of the sibling and its red left child. So sibling becomes red and the left child becomes black. Then we right rotate the sibling node. Then we mirror this. If the node is on the right side and the sibling right child is red, we swap the colors and left rotate sibling node. Then after, we continue by checking for case 6, which is the opposite and covers if the sibling is black with a right red child and a black left child. This time we make the sibling color same of the parent and make parent black. Then if the node is on the left side, we make the sibling right color to be black and left rotate the parent, and do the opposite if node is a right child. Now back to our tree. Note that our node 60 is in perfect position for case 5 since its sibling is black and has a right red child. And since it is on the right side, it will be caught by the second if statement in case 5. So when I remove the sibling and its right child, will swap colors and sibling will be left rotated. This will then make it perfect for case 6, second part, when the node has a black sibling and it is on the right side. We just right rotate the parent, which then make node 30 the new root. Then I'll just go ahead and remove nodes 40 and 30 to finally cover the second part of case 1. When we want to remove the root node, we just go ahead and remove it. I will leave all the rules in the comments below and the link for the code on this video. For more videos like this, like, share, and subscribe. Thanks for watching. Catch you in the next one. Bye-bye.